What phenomena are scientists still trying to explain? Story 1. Some of the most interesting things scientists are still trying to explain aren't just obscure edge cases, they're fundamental parts of reality that we interact with every day or see all around us, but don't fully understand at a deep level, which is what makes this question feel so much bigger the more you think about it. Take something like dark matter, for example, where we can see its gravitational effects shaping galaxies and influencing the structure of the universe, but we still don't know what it actually is, which is kind of unsettling when you realize a huge portion of the universe is made up of something we can't directly detect. And then there's consciousness. Not just brain activity, but the actual experience of being aware, something every person has direct access to. Yet science still can't fully explain how physical processes in the brain translate into subjective experience, which feels like one of the biggest gaps between what we can measure and what we actually feel. You also have things like turbulence in fluids, which sounds simple until you try to model it precisely, or the origin of life, how non-living chemistry transitioned into self-replicating systems, something we know happened but can't fully recreate or trace step by step. And that's what makes this topic stick, because it shows that even with all the progress we've made, there are still layers of reality that remain unresolved, not because we haven't tried, but because they're inherently complex or require new ways of thinking. At the same time, that uncertainty isn't necessarily a limitation. It's part of what drives science forward. Still, it's hard not to feel a certain weight to it, because the more we learn, the more we realize how much we don't. Story 2. Why there is something rather than nothing is one of those questions that sounds simple on the surface. But the more you think about it, the more it kind of breaks your brain, because it's not asking about how things work within the universe. It's asking why the universe exists at all, instead of there being absolutely nothing. And the weird part is that science can get you pretty far, but not all the way. The Big Bang explains how the universe expanded from an extremely hot, dense state, and physics can describe what happened fractions of a second after that, but it doesn't really answer why there was something to expand in the first place, or why the laws of physics exist at all. And once you hit that boundary, things get strange, because even the idea of nothing is hard to define. Is it truly empty, or does it still have rules, potential, structure, something that allows something to emerge? Because if it does, then it's not really nothing anymore. Some theories suggest the universe could arise from quantum fluctuations, where empty space isn't actually empty. But again, that just pushes the question back one step. Why does that kind of system exist at all? Which is where the question starts to feel less scientific and more philosophical, because it might not be something that can be answered through observation or experiment in the usual sense. It's more about the limits of explanation itself. At the same time, there's no clear alternative either. Nothing might not even be a stable state, or it might be impossible in a way we don't fully understand. Still, the question sticks, because it sits at the edge of everything, not just what we know, but what we can even ask. And once you really start thinking about it, it's hard to stop. Story 3. The kinetics of anesthesia is one of those topics that seems like it should be straightforward at first. Like, you give a drug, it binds to a receptor, it does its thing, end of story. But the deeper you go into it, the more it starts to feel like one of those messy intersections between physics, chemistry, and biology, where nothing is as clean as the models make it look. Because on paper, a lot of anesthetics are explained through specific targets. Things like EABA receptors, ion channels, and synaptic inhibition, where drugs enhance inhibitory signaling and basically quiet down neural activity, which makes sense and definitely explains part of what's going on. But then you run into all the weirdness. Different anesthetics with very different chemical structures produce similar effects, potency correlating with lipid solubility in ways that led to things like the Meyer-Overton correlation, which suggests that membrane interactions, not just receptor binding, play a big role. And that's where the non-specific binding question starts to get really interesting. Because if anesthetics are dissolving into lipid membranes and altering their physical properties, like fluidity or thickness, then the effect isn't just about hitting one receptor, it's about changing the environment those receptors exist in, which could indirectly modulate a whole range of proteins at once. But at the same time, there's solid evidence for specific binding too. Certain anesthetics clearly interact with defined sites on proteins, and mutations in those sites can change sensitivity, which argues against it being purely non-specific. So you end up in this weird middle ground. It's not one or the other, it's probably both. Some degree of specific receptor interaction layered on top of broader, more diffuse effects on membrane and protein dynamics. Which is why it feels so frustrating, because you're not missing something obvious. It's just genuinely not fully resolved. And that's kind of what makes it such a good question. It sits right at the edge where reductionist explanations start to break down, and you have to accept that multiple mechanisms can be true at the same time, even if that's a lot less satisfying than a clean answer. Story 4. The way stars orbit galaxies, all moving at roughly the same speed, regardless of how far they are from the center, is one of those observations that feels like it shouldn't happen if you just apply the basic gravity you learn early on, because intuitively, you would expect stars farther out to move slower, the same way planets farther from the sun take longer and move more slowly in their orbits. But when astronomers actually measured it, what they found didn't match that expectation at all. Instead of dropping off, the rotation speeds stay surprisingly flat. Stars way out on the edges of a galaxy are moving almost as fast as those much closer in, which, if only the visible matter were there, should make those outer stars drift away over time. And that's where the problem starts. Because the math doesn't work with just what we can see. There isn't enough observable mass in stars, gas, and dust to generate the gravitational pull needed to keep those outer stars moving that fast and still bound to the galaxy, which is why this leads straight into the idea of dark matter. The current explanation is that galaxies are surrounded by massive halos of invisible matter that don't emit or absorb light, but still exert gravity, effectively adding enough mass to hold everything together and flatten those rotation curves. But that's not the only angle people have explored. Some alternative theories try to modify gravity itself at very large scales, suggesting that our understanding of how gravity behaves might not be complete when you move beyond certain distances or accelerations. And that's what makes this phenomenon stick, because it's not just a small discrepancy, it's something that shows up consistently across galaxies. At the same time, we still haven't directly detected dark matter in a way that fully confirms what it is. So you're left in this strange position. We know something is there, or something about our model is off, but we don't yet have a complete answer. And until that gap is closed, it remains one of those big, open questions, sitting right at the core of how we understand the universe. Story 5. Ball lightning sits in that frustrating space where there are enough credible observations that you can't just dismiss it as imagination, but not enough consistent, repeatable data to pin down exactly what it is, because unlike regular lightning, which is already complex but at least well understood, this shows up as these glowing, floating spheres that can drift, hover, sometimes pass through windows, and then disappear or even explode. And what makes it so tricky is how inconsistent the reports are. Different sizes, colors, durations, behaviors, some lasting a fraction of a second, others lingering for several seconds, which makes it really hard to build a single clean model that explains all cases without stretching the physics a bit. There have been a bunch of attempts to explain it. Some ideas suggest it could be plasma contained by electromagnetic fields. Others point toward vaporized silicon from soil being energized during a lightning strike, creating a kind of glowing, self-sustaining reaction. And there are even theories involving microwave radiation trapping energy in a localized area. And none of them are completely satisfying. Because while some experiments have recreated things that look like ball lightning in controlled settings, they don't fully match the range of behaviors reported in the real world, which is what makes it stick. It's not just rare, it's elusive, hard to predict, hard to capture, and even harder to study in real time. At the same time, it's not supernatural. It's almost certainly some natural, electrical, or chemical process we just don't fully understand yet. Still, the mystery holds, because it's one of those reminders that even in something as studied as lightning, there are still edge cases that don't quite fit. And until we can reliably reproduce and measure it, it stays just out of reach. Story 6, cold welding sounds almost fake the first time you hear it, because the idea that two pieces of metal can just stick together without heat, solder, or any adhesive feels like it goes against everything you expect about how materials behave. But once you get into the physics of it, it actually starts to make uncomfortable amounts of sense. Because metals, at a fundamental level, aren't really solid in the way we intuitively think. They're lattices of atoms with free electrons. And if you can bring two clean metal surfaces close enough together, close enough that there's no oxide layer, no contamination, no air gap, then those atoms don't really know they came from different pieces. They just see neighboring atoms and form bonds. And that's where the catch is. In normal conditions on Earth, this basically never happens accidentally because surfaces are always covered in microscopic layers of oxidation, oils, dust, all kinds of contamination that keep the atoms from ever getting close enough to interact directly. But in environments like space where you have a vacuum and no atmosphere constantly recontaminating surfaces, suddenly that barrier disappears and metals can fuse together just from contact, which is why it became a real concern for satellites and spacecraft components early on. And once you realize that, it flips your intuition a bit. Because it's not that cold welding is some weird special case. It's that normal conditions are what prevent it from happening all the time, which is what makes it stick as a phenomenon. It exposes how much of what we think of as stable, separate objects is actually dependent on invisible layers and conditions we don't usually think about. And once those conditions change, the rules feel like they change with them, even though, technically, they never did. Story 7. Mental illness, when you really sit with how it's understood today, starts to feel less like a clearly mapped out medical field and more like a system of descriptions built around patterns we observe. Because unlike something like a broken bone or an infection, we don't usually have a single clean biological marker we can point to and say, this is the cause. Instead, what we have are classifications. Clusters of symptoms, behaviors, reported experiences, things that tend to appear together often enough that they've been grouped into categories like DSM-5, which helps clinicians communicate and treat patients, but doesn't necessarily explain why those patterns exist in the first place. And that's where the frustration starts to build, because two people can have the same diagnosis and present very differently, or different diagnoses with overlapping symptoms, which makes the boundaries feel less precise than people might expect from something labeled as a disorder. It starts to feel more like mapping the surface of something rather than fully understanding what's underneath. And once you think about it that way, the question shifts. Is it chemical imbalance, neural circuitry, environment, trauma, genetics, some combination of all of those, or something we don't even have the tools to measure yet? And the honest answer right now is probably a mix, which is why treatment often involves trial and adjustment rather than a single targeted fix. At the same time, there's a broader perspective. Even without complete understanding, these classifications still have real value. They help people get support, structure treatment, and make sense of experiences that would otherwise feel chaotic. Still, the idea sticks, because it highlights a gap. We're very good at recognizing patterns, but not always at explaining them. And when it comes to something as complex as the human mind, that gap feels especially noticeable. Story 8, Sleep. when you really stop and think about it, is one of those things that feels so normal you almost don't question it. But the moment you do, it becomes kind of unsettling how essential it is and how incomplete our understanding still is, because every single human being spends a massive portion of their life completely disconnected from the world, vulnerable, unconscious, and yet if you remove it, things start breaking down incredibly fast. At first, it seems straightforward: rest, recovery, energy. But that explanation doesn't fully hold up under scrutiny, because sleep isn't just powering down, it's an active process with distinct stages like REM sleep and non-REM cycles. Brain activity that sometimes looks almost as complex as when you're awake, and functions that go far beyond simple rest. And that's where it gets strange. Memory consolidation, emotional processing, neural pruning, even waste clearance in the brain through systems like the glymphatic system. All of these things happen during sleep, but none of them fully explain why it has to take this form, this full shutdown of consciousness, rather than something more efficient. Because evolution usually favors efficiency, and yet sleep leaves organisms exposed, unable to respond quickly to threats, which suggests whatever benefits it provides must be incredibly important to outweigh that risk. And still, there's no single unified answer. It's not one function, it's many. At the same time, we know what happens without it: cognitive decline, emotional instability, physical health issues, and in extreme cases, death, which makes it clear that sleep isn't optional in any meaningful sense. Still, the mystery sticks, because we can describe what sleep does in pieces, but not fully why it exists in the way it does. And when something takes up a third of your life and remains partially unexplained, it's hard not to find that a little strange. Story 9. The brain is one of those things that feels like it should be understood by now, at least at a high level, because we've mapped regions, identified neurotransmitters, tracked electrical activity, and can even watch parts of it light up in real time. But the deeper you go, the more it starts to feel like we're describing the surface of something without fully grasping what's actually happening underneath. Because on paper, like you said, it's just networks. Neurons, synapses, electrochemical signals, neurotransmitters like dopamine, serotonin, glutamate, all interacting in incredibly complex patterns, which gives the impression that if we just map it precisely enough, the mystery should disappear, but it doesn't. And that's where it gets confusing, because knowing the components doesn't automatically explain the experience. We can trace signals, measure activity, even predict certain responses, but that still doesn't fully explain things like consciousness, why a particular pattern of activity feels like something from the inside, or how subjective experience emerges from what looks, at least externally, like electrical and chemical processes. And the same thing shows up with learning and memory. We understand pieces of it: synaptic plasticity, long-term potentiation, how connections strengthen or weaken over time, but turning that into a complete explanation of how a memory is formed, stored, and recalled as a coherent experience is still not fully solved, which is where the gap becomes really noticeable. Because it's not that we know nothing, it's that we don't have a unifying explanation that connects all the layers. At the same time, there's a broader perspective. Progress is happening, just slowly and unevenly, because the brain is arguably the most complex system we've ever tried to study. Still, the idea sticks, because it highlights something kind of unsettling, that the thing doing the understanding is the same thing we're trying to understand. And that loop makes it hard to ever fully step outside of it and see the whole picture clearly. Story 10. The speed of dark is one of those phrases that sounds simple, almost clever, but the moment you try to pin it down physically, it starts to fall apart in an interesting way. Because unlike light, which is an actual thing traveling through space at a measurable speed, darkness isn't really a thing at all. It's just the absence of light. So, when people ask about the speed of darkness, what they're really asking is how fast light can disappear or be removed from a region, and that ends up bringing you right back to the same limit defined by speed of light, because any change in illumination, whether it's light turning on or off, propagates at that same speed. For example, if you suddenly block a light source, like turning it off or putting something in front of it, the darkness doesn't spread outward as its own entity. What's actually happening is that photons stop arriving, and that change travels outward at the speed of light, which is why shadows move the way they do. They can appear to move faster than light in some cases, but that's just a projection effect, not something physically traveling through space with mass or energy. And that's where the idea gets a bit philosophical. Because darkness feels real to us, it's something we experience directly, but in physics terms, it's defined by what's not there rather than what is. At the same time, the question sticks, because it highlights how our intuition can treat absence like a substance, something that moves, spreads, or exists independently, even when it doesn't in a physical sense. And once you realize that, it kind of flips the way you think about it. There is no speed of dark. There's only the speed at which light changes, and everything else is just how we describe that absence. Story 11. Déjà vu is one of those experiences that feels almost eerie in the moment, like your brain is briefly convincing you that you've already lived through something that you logically know is happening for the first time. And what makes it so strange is how convincing it is, even when you're fully aware that it doesn't make sense. From a scientific perspective, it's often explained as a kind of glitch in memory processing, where the brain momentarily mislabels a current experience as something familiar, almost like the signal for "this is happening now" and "this has already happened" gets slightly out of sync, which creates that weird overlap. There are a few different ideas about how that might happen. One is that there's a tiny delay between different pathways processing the same input. So one part of the brain registers it first, and when the second catches up, it feels like a repeat rather than a continuation. And another involves the temporal lobe, which is heavily involved in memory, sometimes misfiring or activating familiarity circuits without an actual stored memory to match. And that's where it gets interesting, because it's not that you're remembering something real. It's that your brain is generating the feeling of remembering without the content to back it up. At the same time, it's not fully solved. We can describe the mechanisms in pieces, but we don't have a single definitive explanation that covers every case or explains exactly why it feels so specific and immersive when it happens. Still, it sticks because it's one of those rare moments where your sense of time and reality briefly slips, just enough to notice. And when something that fundamental, your perception of now versus before, can glitch even for a second, it makes you realize how constructed that experience really is, even if it usually feels seamless. Story 12. The double slit experiment is one of those things that sounds simple enough when you first hear it, just particles going through two slits and hitting a screen. But the moment you actually look at what happens, it completely messes with your intuition about how reality is supposed to work. Because if you fire particles like electrons one at a time through two slits, you would expect them to behave like tiny bullets, going through one slit or the other and forming two clusters on the screen behind. But instead, what you get is an interference pattern, something you'd normally only expect from waves, like ripples overlapping in water. And that alone is weird. But it gets worse. Because if you try to measure which slit the particle actually goes through, suddenly the interference pattern disappears and it behaves like a particle again, as if the act of observing it changes the outcome, which is where the confusion really kicks in. Because it suggests that before measurement, the particle isn't just going through one slit or the other, it's in a kind of superposition, described by wave-particle duality, where it behaves like a spread-out wave of possibilities rather than a single, definite object. And once you think about that, it starts to feel less like a physics experiment and more like a challenge to how we think about reality itself. At the same time, there are interpretations that try to make sense of it, like the idea that it's not consciousness observing that matters, but interaction with a measuring device, which causes something called decoherence, effectively collapsing those possibilities into a single outcome. Still, the experiment sticks. Because it's not just a theory, it's been repeated and confirmed countless times, and it keeps giving the same answer. That at a fundamental level, reality doesn't behave the way our everyday experience suggests it should, and once you really sit with that, it's hard to go back to thinking of the world as simple or intuitive. Story 13. Turbulence should be solved by now, especially since it shows up in something as familiar as air flowing over a wing or water moving in a river. But the reality is that once fluid motion becomes chaotic, our ability to predict it precisely kind of falls apart in a way that's surprisingly stubborn. Because at the core of it, fluid flow is described by the Navier-Stokes equations, which we've had for a long time, and in theory, they contain everything you need to describe how fluids behave. But in practice, they're incredibly difficult to solve in turbulent regimes. Small changes in initial conditions can lead to wildly different outcomes. Eddies form within eddies, energy cascades across scales, and what starts as smooth, predictable flow suddenly becomes irregular and chaotic in a way that resists simple modeling. And that's where the frustration comes in. Because we can simulate turbulence to a degree, we can approximate it, engineer around it, even predict statistical properties of it, but we still don't have a clean, exact, closed-form understanding of how it evolves in every situation. Which is kind of wild when you think about it, because this isn't some distant cosmic mystery. It's happening every time you pour coffee, every time a plane flies, every time wind moves through trees. At the same time, it's not like we're completely in the dark. We understand the general behavior, the transition from laminar to turbulent flow, energy transfer, dissipation, all of that is mapped out conceptually. Still, the idea sticks, because it sits in this strange place where the equations exist, but the full solution doesn't. And when something so common remains that hard to fully predict, it's a reminder that even familiar parts of the world can hide deep complexity just under the surface. Story 14. The idea that geometry itself can change depending on where you are in the universe is one of those things that feels completely wrong at first, because we're so used to thinking of geometry as fixed, like triangles always adding up to 180 degrees, straight lines being straight, space behaving consistently everywhere. But that intuition only really holds in flat space. Once you start looking at gravity on a large scale, especially through something like general relativity, the picture changes pretty dramatically, because gravity isn't just a force pulling objects together, it's the curvature of space-time itself. And that's where it gets weird. Mass and energy bend space-time, and that bending changes the rules of geometry locally. So in strongly curved regions, like near massive objects or something extreme like a black hole, the shortest path between 2 points isn't what you'd normally think of as a straight line, and angles don't behave the way they would on a flat surface. So you can end up in situations where the angles of a triangle don't add up to 180 degrees, or parallel lines can converge or diverge, depending on the curvature of the space you're in, which is kind of wild when you really sit with it, because it means geometry isn't just an abstract universal truth. It's tied to the structure of the universe itself. At the same time, in most everyday situations, space is close enough to flat that those differences are negligible, which is why our intuition works so well on human scales. Still, the idea sticks, because it flips something very basic, the notion that math describes reality the same way everywhere. And once you realize that even geometry depends on context, it makes the universe feel a lot less rigid and a lot more dynamic than it first appears. Story 15. The Mpemba effect feels like it shouldn't be real, because on a basic level, it sounds like you're saying hot water can freeze faster than cold water, which seems to go directly against common sense and thermodynamics. And yet under certain conditions, it actually does happen, which is why it keeps coming up as one of those annoying edge cases that refuses to go away. The effect itself, known as the Mpemba effect, isn't consistently reproducible in every setup, which is part of what makes it so frustrating, because it depends heavily on conditions like container shape, evaporation, convection currents, dissolved gases, and even how the water was handled beforehand. And your idea about volatile particles or dissolved substances being boiled off is actually one of the more plausible contributing factors. When you heat water, you drive off dissolved gases and can change the composition slightly, which might affect how it cools and freezes, especially in terms of nucleation, and how easily ice crystals start forming. But that's only one piece of it. Evaporation can reduce the volume of the hot water, meaning there's simply less water left to freeze. Convection currents in hotter water can redistribute heat more efficiently, and in some cases, supercooling plays a role where colder water can actually stay liquid below freezing longer than hotter water under the right conditions, which is why there isn't a single clean explanation. It's not one mechanism. It's a combination that sometimes lines up just right. Still, the effect sticks, because it's one of those rare cases where everyday intuition fails in a very visible way. And even though we can explain parts of it, we still don't have a simple universal rule that predicts exactly when it will happen, which makes it just confusing enough to keep people thinking about it. Story 16. The origin of life feels like it should have a clear answer by now, especially given how much we understand about chemistry and biology separately. But the moment you try to connect the two, going from non-living molecules to something that can replicate, evolve, and sustain itself, it becomes this massive gap that we still haven't fully bridged. Because we know the ingredients, early Earth had water, organic molecules, energy sources like lightning or hydrothermal vents, and under the right conditions, chemistry can get surprisingly complex, forming amino acids, nucleotides, and other building blocks. But the jump from that to actual life is where things get difficult. How do you go from random chemical reactions to something like self-replication? Something that not only exists, but can copy itself with enough accuracy to persist and enough variation to evolve? That's where ideas like the RNA world hypothesis come in, suggesting that RNA might have been an early molecule capable of both storing information and catalyzing reactions, acting as a kind of bridge between chemistry and biology. But even that doesn't fully solve it, because you still need a system where these molecules are stable, concentrated, and interacting in the right way, maybe inside primitive membranes or compartments, which adds another layer of complexity, and that's what makes it so tricky. It's not one step. It's a chain of unlikely steps that somehow happened. At the same time, there's progress. Experiments have shown that some of these building blocks can form under plausible early Earth conditions, and simple self-organizing systems are possible. Still, the question sticks. Because until we can recreate that transition from non-life to life in a clear, repeatable way, there's always going to be that gap. And when you realize that every living thing traces back to that one transition, it starts to feel less like a scientific detail and more like the biggest unanswered question of all. Story 17. The Hessdalen lights feel almost too consistent to dismiss, but still too unpredictable to fully explain, because unlike a lot of one-off sightings, these lights have been reported repeatedly in the same area, specifically in Hessdalen, over decades, which makes them harder to write off as simple misidentifications or isolated events. People describe glowing orbs, sometimes white, sometimes yellow or red, hovering, drifting, or moving in ways that don't always match conventional aircraft or natural light sources. And what makes it even more interesting is that they have actually been studied with instruments, radar, cameras, and sensors, not just eyewitness accounts. And still, there's no single explanation that covers everything. Some researchers think it could be related to ionized gas or plasma, possibly created by geological activity in the valley, like mineral-rich dust, interacting with the atmosphere, and becoming electrically charged under certain conditions. Others suggest combustion processes, like dust clouds burning slowly in the air, or even piezoelectric effects from stress in the surrounding rocks generating electrical discharges. And none of these are completely satisfying, because while they can reproduce some aspects of the lights in controlled experiments, they don't fully explain the range of behaviors reported, especially the more structured or long-lasting appearances, which is what makes it stick. It's not just a mystery in the sense of we don't know. It's a mystery where we have data, observations, and hypotheses, but no unifying answer that ties it all together cleanly. At the same time, it's almost certainly natural. Not something supernatural or alien, but a combination of environmental conditions that we don't fully understand yet. Still, it lingers, because it's one of those rare cases where something visible, repeatable, and relatively accessible still resists explanation. And that makes it feel just a little more real, and a little more frustrating. Story 18. Earthquake lights sit right on the edge between anecdote and observation, because they have been reported for centuries, long before modern instruments. And yet even today, when we do catch them on camera, they still don't neatly fit into a single explanation. People describe blue or white flashes, glowing orbs, sometimes even sheet-like illumination in the sky, appearing just before or during seismic events, which already makes them feel connected to something deeper in the Earth, rather than just atmospheric coincidence. And that's where the main theories start to cluster. One of the more discussed ideas is tied to the piezoelectric effect, where certain rocks under extreme stress, especially quartz-bearing ones, can generate electrical charges as they deform, potentially leading to ionization of the air and visible light. There are also theories about gases being released from the ground, like radon or other ionized particles, interacting with the atmosphere and producing glow or flashes, or even localized electrical discharges similar to static buildup on a massive scale. But none of these fully explain everything, because the reports vary so much. Different colors, different durations, different timing relative to the quake itself, sometimes before, sometimes during, sometimes even after, which is what makes it frustrating from a scientific standpoint. It's not that we have no ideas, it's that we don't have one that consistently works across all cases. Still, the phenomenon sticks, because it's not just folklore anymore. There are documented instances, video evidence, instrument readings, enough to say something real is happening, even if we don't fully understand the mechanism yet. And when the Earth itself seems to produce light under stress, it's hard not to feel like we're still missing a piece of the picture, something happening beneath the surface that only occasionally reveals itself in a way we can actually see. Story 19. European eel migration is one of those biological mysteries that feels like it should be solved by now, especially after more than a century of research, tagging, and tracking. But the deeper you look, the more it feels like we're still piecing together fragments of a story without ever seeing the full picture. The species itself, European eel, has this incredibly strange life cycle where it grows up in rivers and lakes across Europe, then at some point transforms into a migratory form and heads out into the open ocean, traveling thousands of kilometers toward the Sargasso Sea, which is believed to be its spawning ground. And that part, at least in theory, is well established. But here's where it gets weird. No one has actually observed adult eels spawning there. No one has found eggs. What scientists have found are larvae called leptocephali, drifting back toward Europe, which strongly suggests that spawning is happening somewhere in that region, but the exact where, when, and how remains frustratingly out of reach. And then there's the navigation problem. How do eels that have never made the journey before find their way across an entire ocean? There are hypotheses involving magnetic fields, ocean currents, temperature gradients, maybe even chemical cues, but nothing that fully explains the precision of it, which is what makes the whole thing stick, because it's not just one unanswered question, it's several layered together. Where exactly do they spawn? Why has it never been directly observed? How do they navigate so accurately? And why does the life cycle depend on such a complex, long-distance loop in the first place? At the same time, tracking technology is improving, and we're getting closer, step by step. Still, the mystery hasn't fully cracked. And when an animal can cross an ocean, reproduce, and disappear from direct observation entirely, it's hard not to feel like we're still missing something fundamental about how it all works. Story 20. Ultra-weak photon emissions come off less like a fringe curiosity and more like a quiet, measurable feature of life once you look at the data. Because across plants, animals, and even single cells, there's this constant, extremely faint release of light that only shows up when you use sensitive instruments, and yet it tracks closely with whether something is alive or not. What's being observed, often called biophoton emission, is tied to normal metabolic activity, especially oxidative reactions where molecules get excited and then release tiny packets of energy as photons when they settle back down, which fits well with what we know about chemistry, but doesn't fully explain the structure of what's being detected, because it's not always random. In some experiments, the emissions show patterns, timing, even a kind of weak coherence that doesn't quite behave like simple background noise, which is where things start to get interesting. It raises the question of whether this light is just a side effect of metabolism, or if it's somehow integrated into how cells function. There have been ideas about it playing a role in cellular signaling, possibly as an additional layer alongside chemical and electrical communication, but that's still very much in the exploratory stage and not widely accepted as a core mechanism. At the same time, the grounded explanation still holds strong. We know biological processes can generate photons. We can measure them, we can correlate them with activity, but turning that into a clear functional role is where things get uncertain. And that's what keeps it interesting. It sits right in that space where we understand the source, but not the full significance. And when something as fundamental as metabolism quietly produces light, it suggests there are still layers of biology we haven't fully unpacked yet. Story 21. Earth's 26-second hum is one of those signals that feels almost artificial when you first hear about it. Because the idea that the planet itself is producing a steady repeating pulse every 26 seconds sounds more like a machine than a natural system, and yet it's been consistently picked up by seismometers for decades. The signal has been traced to a region in the Gulf of Guinea, off the west coast of Africa, which at least narrows down where it's coming from, but not exactly why it's happening, and that's where things start to split into competing explanations. One of the leading ideas is that it's tied to ocean waves interacting with the continental shelf, where constant wave pressure could generate rhythmic seismic vibrations that propagate through the Earth, kind of like a natural resonance effect. Another possibility is more geological, pointing to volcanic or magmatic activity beneath the seafloor, where periodic movement or pressure changes could produce a repeating signal. And both explanations make sense on their own, but neither fully explains why the pulse is so regular, so persistent, and so stable over long periods of time, which is what makes it stick. Because this isn't a one-time anomaly, it's ongoing, predictable enough to measure, but not fully understood. At the same time, it's clearly natural. There's no indication of anything artificial, just a process we haven't fully pinned down yet. Still, it leaves this odd impression that the Earth isn't just passively sitting there, it's constantly moving, vibrating, producing signals at scales we don't normally notice. And every now and then, one of those signals stands out just enough to remind us that there's still a lot going on beneath the surface that we don't fully understand. Story 22, the Devil's Kettle, is one of those natural features that feels almost designed to provoke curiosity because it takes something as familiar as a river and then just breaks the expectation in half, literally, with one side continuing normally while the other seems to vanish entirely. Located in Judge C.R. Magny State Park, the Brule River splits at the waterfall, with one stream flowing downstream as expected, while the other drops into this deep, swirling pothole known as the kettle, which, for a long time, appeared to have no visible outlet. And that's where the mystery built up. People threw in dye, ping pong balls, even tracked objects, trying to see where the water would emerge, but nothing obvious showed up downstream, which led to all kinds of speculation, underground caverns, hidden channels, even the idea that the water might be going somewhere completely unexpected. But here's where it gets interesting. More recent studies have shown that the volume of water entering the kettle and the volume continuing downstream eventually balance out, suggesting that the missing water is almost certainly rejoining the river system somewhere below, likely through underground pathways in the rock. So, it's not that the water disappears, it's that the route it takes isn't directly visible. Still, the phenomenon sticks, because even when you know the likely explanation, it doesn't feel resolved when you're standing there watching half a river vanish into a hole with no clear exit. And that gap between what's probably happening and what you can actually see is what keeps it feeling like a mystery. Story 23, Eternal Flame Falls, is one of those places where the explanation gets almost complete, but not quite, which is what keeps it interesting, because on the surface it sounds straightforward. A small flame burning behind a waterfall, fueled by natural gas seeping out of the rock, something that does happen in other parts of the world. It's located in Eternal Flame Falls, tucked inside a grotto behind the falling water, where you can actually see a small, steady flame flickering in a spot that feels like it shouldn't support combustion at all. And the basic mechanism is known. There is natural gas, primarily methane, seeping from the shale beneath the falls, which feeds the flame when it's lit. But that's where the confusion starts, because in most cases, methane like that is produced through higher temperature processes deep underground, where heat breaks down organic material over long periods. Here, the shale formation doesn't appear to be hot enough for that standard explanation to fully apply, which leaves a gap. Some researchers think there could be unusual low-temperature chemical reactions happening, or that the rock composition allows gas to form or accumulate in ways that aren't typical, possibly involving catalytic processes that haven't been fully characterized. Others suggest the gas might be migrating from deeper source through fractures, even if the immediate area doesn't show the expected conditions. And none of these explanations fully settle it. Because while we know what is happening, gas is feeding a flame, we don't fully understand why it's happening here under these specific conditions. And that's what makes it stick. It's not a complete mystery, but it's not fully solved either. And when something as simple as a flame depends on geology that doesn't quite follow the usual rules, it leaves just enough uncertainty to keep it fascinating. Story 24. Morning glory clouds feel almost engineered when you see them, because instead of the usual chaotic, shifting shapes of clouds, you get these long, perfectly formed cylinders stretching across the sky, sometimes up to 1,000 kilometers, moving like a slow, continuous wave. They're most famously observed in Gulf of Carpentaria, where pilots and observers have documented them for years. And what's especially striking is how stable they appear, maintaining their structure over huge distances without just breaking apart like most cloud formations would. And that's where physics gets tricky. They're generally understood as a type of atmospheric wave, similar to a soliton, where a disturbance travels through the air and maintains its shape due to a balance between forces. In this case, differences in air pressure, temperature layers, and wind patterns. But even with that framework, the full picture isn't clean, because the conditions required to form them are very specific, involving sea breezes, temperature inversions, and the interaction of air masses in just the right configuration. And even then, we don't fully understand why the structure remains so coherent for so long instead of dissipating like most waves in the atmosphere, which is what keeps them interesting. We can describe the ingredients, we can model parts of the behavior, but we can't always predict exactly when or how they'll form, or fully explain their persistence. And when something as dynamic as the atmosphere produces a structure that looks almost perfectly ordered, It feels like we're seeing a balance of forces that we understand in pieces, but not completely as a whole. Story 25, the space roar, is one of those signals that feels almost absurd when you first hear about it, because the idea that there's a background radio noise coming from the universe that's several times stronger than what all known galaxies can account for doesn't just suggest a missing piece, it suggests we might be missing something big. It was picked up in 2006 by instruments designed to measure cosmic radio waves, including data from NASA missions. And what stood out wasn't just that the signal existed, but that it was uniform, coming from all directions rather than a single identifiable source, which immediately rules out a lot of simple explanations. And that's where the problem starts. Because if it's coming from everywhere, it's likely something distributed across the universe, not a single object or event. But when scientists tried to add up all known radio sources, galaxies, quasars, known emissions, it still fell way short of explaining the intensity of the signal, which leaves a gap that hasn't really been closed. There have been attempts to explain it. Maybe there's a population of faint, distant radio sources we haven't resolved yet. Maybe something about early galaxy formation produced more radio noise than expected. Or maybe there's some kind of diffuse process happening on a large scale that we don't fully understand. But none of these explanations fully match the data, which is what makes it stick. Because this isn't just a weird one-off signal, it's a persistent background, something woven into the structure of the observable universe. And when the total output of everything we know still isn't enough to explain what we're measuring, it leaves you with that uncomfortable feeling that there's something out there contributing to it that we haven't identified yet. Story 26, the 2026 fireball surge, stands out because it's not just about isolated sightings. It's the apparent increase in frequency and intensities over a short period that makes it feel different from the usual background of meteor activity, especially since it doesn't clearly match up with established meteor showers that scientists already understand pretty well. Under normal conditions, bright meteors, or fireballs, show up sporadically or cluster around predictable events tied to known debris streams. But this wave seems more scattered and persistent, which is why researchers are trying to figure out whether it points to a specific source or something more general. One possibility is that Earth has intersected with a previously untracked stream of debris, maybe from a fragmented comet or asteroid, which would temporarily increase the number of large objects entering the atmosphere. Another angle is that this could reflect changes in detection rather than actual frequency, with more ground cameras, satellites, and public reporting making events that were once missed now visible and recorded, but there's still a gap. Because if the increase is real, not just observational, then it raises questions about where this material is coming from and how long it might persist, which is where things remain unresolved. Scientists need consistent trajectory data, composition analysis, and time correlation across different regions to determine whether this is a localized spike, a short-lived event, or something more systemic. And until that picture becomes clearer, it sits in that uncomfortable middle ground, not fully explained, but not random enough to ignore, just enough of a pattern to suggest that something is happening, even if we don't yet know exactly what. Story 27. Saturn's rings don't just sit there as static bands of ice and dust. They behave more like a dynamic system, constantly shifting, interacting, and in some cases literally vibrating, which is what made the data from the Cassini-Huygens so surprising when scientists started noticing these organized, wave-like ripples moving through the rings. What they found were patterns that looked a lot like harmonics, almost like the rings were responding to something beneath or within Saturn itself, similar to how a surface can ripple in response to vibrations you can't directly see. And that's where it gets really interesting, because one of the leading ideas is that these waves are being driven by oscillations inside the planet, essentially Saturn ringing like a bell, with variations in its internal structure creating gravitational tugs that propagate outward and imprint themselves onto the rings. But that explanation isn't fully locked in. there are still questions about whether all the observed patterns can be explained purely by gravity, or if other factors, like magnetic field interactions or plasma effects, might also be playing a role in shaping these ripples, which is what keeps it open. Because we're not just looking at the rings anymore, we're using them as a kind of detector, a visible surface responding to invisible processes happening deep inside a gas giant we can't directly observe. And that's what makes it stick. It turns the rings into a diagnostic tool for something hidden, a way of seeing the interior of Saturn through motion rather than direct measurement. And until those signals are fully decoded, they're less like a solved phenomenon, and more like a message we're still trying to interpret. Story 28, Star Jelly is one of those reports that sits in this strange overlap between folklore and modern observation, because it's been described for centuries, often appearing after meteor sightings. Yet when samples are actually collected and tested, they don't consistently point to a single clear origin. The substance itself, often referred to as star jelly, is typically described as translucent, gelatinous, sometimes quickly evaporating or breaking down after being found, which already makes it difficult to study in a controlled, repeatable way. And that's where the confusion starts to stack up. Some explanations suggest it could be biological, things like frogs or toad spawn that have been expelled or left behind, and then swell with moisture, giving that sudden, unfamiliar appearance. Others point to cyanobacteria or slime molds, which can form gelatinous masses under certain conditions. But the meteor connection is what keeps it from feeling fully resolved, because people often report finding it right after seeing something fall from the sky, which creates the impression that it's linked to whatever just passed overhead. At the same time, that link might be coincidental. Bright meteors draw attention to the sky and surroundings, making people more likely to notice unusual things on the ground that would otherwise go ignored. Still, not every sample has been easily classified. Some tests have come back inconclusive or inconsistent, which keeps the door open just enough. And that's what makes it stick. It's not clearly extraterrestrial, but it's not cleanly explained either. Just enough ambiguity, just enough pattern to keep it hovering between explanation and mystery. And when something shows up, disappears quickly, and resists consistent identification, it tends to linger in that space a little longer than most phenomena. Story 29, non-coding DNA, used to be written off as junk, but the more it's studied, the more that label starts to feel like a placeholder for, we don't fully understand this yet. Because while only a small percentage of the genome directly codes for proteins, the rest isn't just sitting there doing nothing. A lot of it is now known to be involved in regulation, turning genes on and off, controlling when and where proteins are produced, shaping development, timing, and response to the environment, which already makes it far more important than the old label suggested. Elements like enhancers, silencers, and non-coding are, as all fall into this category, and they interact in ways that are incredibly complex, forming networks that influence how genes behave, rather than just what they encode. And that's where things start to get difficult. Because mapping genes is one thing, mapping regulation is another entirely. You're not just dealing with sequences, you're dealing with timing, context, cell type, interactions across different regions of DNA that can be far apart but still influence each other, which is why such a large portion of the genome still feels unexplained. Not because it's empty, but because its function isn't straightforward. Some regions might be structural, some regulatory, some evolutionary remnants that still have subtle effects we don't fully detect yet. At the same time, progress is happening. Techniques like CRISPR and advanced sequencing are starting to reveal how these regions behave, piece by piece. Still, the idea sticks, because it flips an old assumption that most of our DNA was useless, and replaces it with something more unsettling, that most of it matters, we just don't fully know how yet. And when the majority of something so fundamental remains only partially understood, it leaves a lot of room for discovery. Story 30, what's being described here isn't just normal tectonic activity, it's something deeper and slower, almost like parts of a continent's foundation are being quietly eroded from below, which is why it's getting so much attention, because cratons are supposed to be the most stable, long-lived parts of Earth's crust. These ancient cores, like the North American craton, have survived for billions of years, resisting the kind of recycling and deformation that affects younger crust. So, the idea that they're actually thinning or dripping downward into the mantle changes how stable we think continents really are. And the mechanism behind it is what makes it even more interesting. The Farallon Plate, which has been subducting beneath North America for tens of millions of years, didn't just disappear cleanly. Parts of it are still sinking deep into the mantle, and as it goes, it appears to be dragging or destabilizing sections of the overlying lithosphere. This process is sometimes described as cratonic thinning, or even dripping, where dense material from the base of the continent becomes unstable and starts to sink downward. And once that starts happening, it's not something you would notice directly. It's incredibly slow, happening over millions of years. But the implications are pretty big, because it suggests that even the most stable parts of continents aren't permanently fixed. They can be modified, weakened, reshaped from below in ways we're only now starting to detect with seismic imaging. At the same time, there's still uncertainty. We can see the structures, model the processes, but the exact dynamics, so how widespread it is, how fast it's happening, and what long-term effects it might have are still being worked out. And that's what makes it stick. It shifts the perspective, from continents as rigid, permanent features, to something more dynamic, slowly evolving even at their deepest levels. And once you realize that the ground beneath entire continents can change over time, it makes Earth feel a lot less static than it appears on the surface. Story 31, the so-called Lake Michigan Stonehenge. Sounds dramatic at first, but once you look at what was actually found, it becomes less about a mysterious monument and more about how creative early humans were with the environment around them, especially in a landscape that looked very different 10,000 years ago. The structure was identified through sonar scans in Grand Traverse Bay, revealing a long alignment of stones leading toward a circular arrangement, which immediately caught attention because it resembles intentional placement rather than random geology. And that's where the speculation started. Anything circular made of stones tends to trigger comparisons to things like ritual sites or ancient monuments. But in this case, the more grounded explanation is actually more interesting in its own way. Researchers now think it may have been a prehistoric hunting feature, essentially a drive line, where stones were arranged to guide or funnel animals like caribou into a specific area, making them easier to hunt. And when you consider the context, it makes sense. Back then, water levels were lower, meaning that area would have been dry land, part of a migration route rather than the bottom of a lake. So what looks submerged and mysterious today would have been fully accessible terrain to the people who built it, which is where the perspective shifts. Because instead of being a symbolic or spiritual structure, it becomes practical, strategic, almost like an early form of environmental engineering. At the same time, not everything about it is fully settled. There are still questions about the exact layout, how it was used, and whether there were additional features that haven't been mapped yet. Still, it sticks, because it's one of those cases where something hidden for thousands of years reappears in a completely different context. And what first looks like a mystery turns into a glimpse of how people adapted to their world long before recorded history. Story 32. The Kola Super Deep Borehole is one of those projects where reality didn't just fail to meet expectations. It actively pushed back harder the deeper we went. Because on paper, drilling into Earth's crust seems like a straightforward extension of what we already do. But once you reach extreme depths, the conditions stop behaving the way models predict. At the site of Kola Super Deep Borehole, scientists managed to drill over 12,000 meters down, which is already incredible. But what really stopped progress wasn't just the depth, it was the temperature. Instead of following the expected geothermal gradient, the heat increased much faster than anticipated, roughly around 60 degrees Fahrenheit, which doesn't sound extreme until you realize how quickly that compounds at depth. And that's where things started to break down. The rock didn't behave like solid, brittle material anymore. It began to act more like plastic, softening under the combined pressure and heat, making drilling unstable and difficult to control. Equipment struggled, structures warped. Progress slowed to the point where continuing became impractical, which is where the bigger question comes in. Because we thought we had a decent understanding of how temperature increases with depth, but this showed that local geology, fluid presence, and pressure conditions can alter that gradient in ways that aren't fully predictable. And it highlights a deeper issue. We've barely scratched the surface of our own planet. Even at 12 kilometers, which is tiny compared to Earth's total radius, conditions have already become extreme enough to stop us. Still, the project sticks in people's minds because it represents a limit, not of ambition, but of the environment, a point where the Earth itself becomes too hostile to easily explore. And when going deeper turns solid ground into something that behaves almost like a slow-moving fluid, it's a reminder that what we stand on isn't as rigid as it seems. Story 33. The Wallace Line is one of those boundaries that you can't see on a map unless someone draws it for you. But once you know it's there, it starts to feel almost uncanny how sharply it divides the natural world, because on one side you get animals typical of Asia, and on the other, species that clearly belong to Australia's evolutionary history, even though in some places the gap between islands is surprisingly small. It runs through the Malay archipelago and was first identified by Alfred Russel Wallace, who noticed that crossing from one island to another could feel like stepping into a completely different ecosystem, despite the short distance. And the broad explanation makes sense. These islands sit on different continental shelves, Asia on one side, Australia on the other, separated by deep ocean trenches that have existed for tens of millions of years, which means that even during periods of low sea level, when land bridges formed elsewhere, these gaps stayed deep enough to prevent easy crossing. But that only explains part of it, because even today, with relatively narrow stretches of water between some islands, many species still don't cross, or do so very rarely, which raises the question of why the boundary remains so strict, even when the physical distance doesn't seem that extreme. And that's where things get more subtle. It's not just distance, it's ecology, competition, climate, evolutionary history, and the fact that species adapted to one side may simply not survive still on the other, even if they manage to get there, which makes the line less like a wall and more like a filter. Still, it sticks as a phenomenon because it shows how invisible boundaries can shape the distribution of life in very real ways. And when two completely different biological worlds can exist side by side with only a thin strip of water between them, it highlights how history, geography, and evolution can lock patterns in place for millions of years, even when, on the surface, it looks like nothing is stopping them. Story 34, Lluvia de Peces, or the Rain of Fish, is one of those events that feels almost mythical until you realize it's been reported repeatedly in the same place, to the point where it's basically part of local tradition, especially in Euro, where people claim that after strong storms, fish are found scattered across the ground. And what makes it harder to dismiss is that it's not just stories. There are modern accounts, photographs, and consistent timing, usually linked to heavy rainfall events, which suggests there's some kind of real, repeatable mechanism behind it. The most grounded explanation involves waterspouts or strong updrafts. The idea is that powerful storm systems can lift small aquatic animals, like fish, from shallow waters, rivers, or coastal areas, carry them through the air, and then drop them elsewhere when the storm weakens. And in theory, that works. We know storms can transport objects over long distances. We know unusual things can fall from the sky during extreme weather. But there are still gaps, because in some cases, the fish found are all of similar species, sometimes even species that don't clearly match nearby water sources. and the events seem very localized rather than widespread, like you might expect from a large storm system, which is where the mystery lingers. Is it purely atmospheric transport? Is there a specific geographic setup that makes it happen repeatedly in the same place? Or is there some local environmental factor that hasn't been fully identified yet? At the same time, it's almost certainly natural. There's no real evidence pointing to anything beyond unusual but explainable weather phenomena. Still, it sticks. Because when something as specific as fish starts falling from the sky, even if you can explain it in theory, it doesn't stop it from feeling just a little surreal when it actually happens. Story 35. The Fosse d'Yon is one of those places where the mystery isn't that water exists or flows, it's that we can't fully trace where it comes from, even after centuries of curiosity and modern attempts to map it out, which is what keeps it sitting in that uncomfortable space between understood and unresolved. Located in Fosse d'Yon, it's this deep circular spring that has been used since Roman times, constantly flowing, clear and steady, which already tells you there's a large and reliable underground system feeding it. And that's the key part. Because the source isn't a single pipe or channel you can just follow, it's part of a complex karst network, water moving through limestone, dissolving paths, creating caves, branching routes that can twist, split, and reconnect in ways that are incredibly hard to map. Divers have actually tried to explore it multiple times, and that's where it gets serious. The passages are narrow, dark, and disorienting, with strong currents and multiple branches, and tragically, several divers have died attempting to trace it, which is why access is now restricted. And even with modern tools, we still don't have a complete map. We know water likely travels long distances underground before emerging there, possibly from multiple sources, but the exact pathways, connections, and full extent of the system remain only partially understood, which is what makes it stick. Because it's not some distant or abstract mystery, it's a physical place you can stand next to, watching water flow out of something we can't fully see into. And when something as fundamental as a spring, something that seems so simple on the surface, is actually connected to a hidden system we can't completely trace, it's a reminder of how much of the world still exists out of sight, even in places we've known about for thousands of years. Story 36, Antarctica's so-called gravity hole, isn't actually a literal hole, but it does point to something very real and very strange, which is a massive dip in Earth's gravitational field detected over a region of the continent. Something that shows up clearly when scientists map gravity variations from satellites. This anomaly, often referred to as the Wilkes Land Gravity Anomaly, sits beneath the ice in East Antarctica. And what makes it unusual is its scale. It's huge, and it suggests that something beneath the surface is denser or structured differently than the surrounding crust. And that's where the theories start branching out. One of the leading explanations is that it could be the remnant of a massive ancient impact crater, possibly from a meteor strike hundreds of millions of years ago, which would have altered the crust and mantle structure in a way that still affects gravity today. Another idea is more geological. It could be related to mantle processes like dense material pooling or sinking beneath the crust, changing how mass is distributed in that region over long time scales. But the problem is access. Everything is buried under kilometers of ice, which means we can't just drill or directly observe what's down there easily. So, most of what we know comes from indirect measurements, gravity data, seismic imaging, and modeling. And that leaves room for uncertainty. Because while the anomaly is real and well documented, the exact cause hasn't been definitively confirmed. Still, it sticks, because it's a reminder that even on Earth there are large-scale features we can detect, but not fully explained. And when an entire region of a continent shows a measurable difference in something as fundamental as gravity, it suggests there's a hidden structure beneath the surface that we haven't fully uncovered yet. Story 37. Prototaxites is one of those fossils that completely messes with your expectations of what early life on land was supposed to look like, because instead of small, simple organisms hugging the ground, you have these massive trunk-like structures, sometimes over 8 meters tall, standing upright hundreds of millions of years ago when nothing else remotely comparable existed. The organism itself, known as Prototaxites, lived around 400 million years ago, long before trees as we know them evolved, which already makes it strange because it looks like a tree trunk but doesn't fit neatly into any modern category, and that's where the confusion really begins. For a long time, scientists debated what it even was. Some thought it was an early tree. Others suggested it was a giant fungus. More recent evidence leans toward a fungal or fungus-like organism based on its internal structure and chemical signatures, but even that doesn't fully settle it, because nothing alive today is quite like it. A fungus growing to that size, forming these towering spires in a landscape otherwise dominated by low vegetation, feels almost alien compared to modern ecosystems, which raises more questions. Why did it grow so large? What ecological role did it play? Why don't we see anything similar today? And what conditions allowed something like that to exist in the first place? At the same time, we do have pieces of the puzzle. Isotope analysis suggests it wasn't photosynthetic, supporting the idea that it fed on decaying organic matter, like fungi do. Still, the full picture isn't complete, because even if we accept that it was a fungus, it was a very unusual one, and that's what makes it stick. It's not just a mystery about classification. It's a glimpse into a version of Earth that operated under very different rules, where something that looks impossible today was once completely real. Story 38, Schumann resonance spikes are one of those things that sit right at the intersection of well-understood physics and messy real-world variability, because the underlying phenomenon itself isn't mysterious at all. But the sudden changes or spikes people talk about are where things get less clear. At the core, the Schumann resonances are natural electromagnetic standing waves that exist between Earth's surface and the ionosphere, mostly driven by global lightning activity, which basically turns the planet into a kind of resonant cavity. Under normal conditions, these frequencies are pretty stable, but what people refer to as spikes are sudden increases in amplitude or shifts in intensity, not the frequency itself jumping wildly, but the strength of the signal changing. And that's where the explanations start to branch out. The most grounded cause is simply changes in global lightning patterns, more storms, more energy being pumped into the system, which naturally increases the signal strength. There are also influences from solar activity, geomagnetic disturbances, and ionospheric conditions, all of which can affect how these waves propagate and resonate. But the confusion comes from interpretation. Because the data can look dramatic, sharp peaks, unusual patterns, and without context, it's easy to assume something fundamentally new or unknown is happening, which is where things tend to get exaggerated. In reality, while the exact combination of factors behind any specific spike isn't always fully mapped out in detail, the general mechanisms are known and consistent with atmospheric and electromagnetic physics. Still, it sticks, because it's one of those cases where a real, measurable phenomenon gets wrapped in layers of interpretation. And when you see sudden changes in something tied to the entire planet's electromagnetic behavior, it's hard not to feel like something significant is happening, even if the explanation is more grounded than it first appears. Story 39, the Black Sea's abyssal preservation, is less about something mysterious happening at the moment and more about a very unusual set of conditions that have stayed stable for a long time, creating an environment where decay just doesn't happen the way you'd expect. What makes the Black Sea unique is that its deep waters are almost completely anoxic, meaning they lack oxygen, and that changes everything about how organic material breaks down once it sinks below a certain depth. Normally, in oxygen-rich environments, bacteria and scavengers quickly decompose anything organic: wood, bodies, shipwrecks. But in the Black Sea's deeper layers, those processes are largely absent. Instead, the water is rich in hydrogen sulfide, which creates conditions that are hostile to most life forms that would otherwise contribute to decay. And that's where preservation comes in. Ancient shipwrecks, some over 1,000 years old, have been found remarkably intact, with wooden structures, ropes, even details that would normally be long gone in other marine environments, which is what makes it feel almost unnatural at first, because we're used to erasing things. But here, time slows down in a very specific way. At the same time, the mechanism itself is understood in principle. It's the layering of the sea, with oxygenated water near the surface and dense, stagnant oxygen-poor water below, that prevents mixing and maintains those conditions. Still, there are details that researchers are still working through. How stable that layering has been over long periods, how it might change with climate shifts, and how exactly different materials interact with that environment over centuries. And that's what makes it stick, not because it's completely unexplained, but because it creates a kind of natural archive, a place where the past doesn't disappear as quickly as it should. And when entire ships can sit on the seafloor, largely untouched for centuries, it feels like time itself is behaving a little differently down there. Story 40. The Great Dissonance isn't a single phenomenon in the way something like turbulence or lightning is. It's more like a pattern people have started noticing across multiple fields, where different layers of reality, physics, biology, perception, don't quite line up as cleanly as we expect them to. It shows up in subtle ways. The gap between what the brain does physically and what consciousness feels like. The mismatch between quantum behavior and classical intuition. The way systems that should be predictable become chaotic or emergent when scaled up. And none of these are unsolved in isolation, but when you look at them together, there's this underlying sense that our models describe pieces of reality really well, but don't always connect into a single unified picture, which is where the dissonance idea comes in. Because instead of one coherent framework, it can feel like we're using different rule sets depending on the scale or context. Quantum mechanics for the very small, relativity for the very large, neuroscience for the mind, each internally consistent, but not fully reconciled with each other. And that creates this kind of conceptual tension. Not a contradiction exactly, but not a seamless fit either. At the same time, it's important to stay grounded. The Great Dissonance isn't an established scientific term. It's more of a way of describing that feeling of fragmentation in our understanding, rather than a formally defined problem researchers are trying to solve. Still, the idea sticks, because it captures something real, that even with all our progress, there are still gaps not just in what we know, but in how the things we know connect. And when your best theories work perfectly in their own domains, but don't quite merge into one unified explanation, it leaves that lingering sense that there's a deeper layer we haven't reached yet.